Hello, Math 1224. This is lesson launch 17.3. This short video, assuredly going to be short. If it's not short, I'm going to redo it. The purpose of this video is to just say a bit more about Taylor polynomials and what they look like when we are trying to approximate a function near some point other than x equals 0. So first, just by way of review, the Taylor polynomial of degree n at x equals 0 for the function f is the sum from, let's see, from k equals 0 to n. I was about to use n as the index of summation, but I've already fixed it here, which means I can't use it as my index of summation anymore. So anyway, the Taylor polynomial of degree n at x equals 0 for function f, assuming, of course, that f is continuous, differentiable. It has to be differentiable n times in order for us to be able to do this. But anyway, that polynomial is the sum from k equals 0 to n of the kth derivative of f evaluated at 0 over k factorial times x to the k. And that may look kind of funny when you look at it that way, but because this is a sum with finitely many terms from k equals 0 to n, this is a polynomial of degree n whose derivatives, whose 0th through nth derivatives at x equals 0 match those of f. And that's something that now you can actually verify. I mean, you could take that polynomial there. You could unpack the summation notation if you wanted to. You could take its derivatives and verify for yourself that the 0th derivative at 0 is just f of 0. The first derivative at 0 is f prime at 0, and so on. Okay, so what if the center is something other than 0? I'm just going to state this as a fact. I'm not going to go to much trouble to try to prove it here, because the work is really the same as what we did in the other videos. I just didn't want to have a bunch of x minus a's in the way while we were doing that. Okay, so here's what changes. So this is now a new definition. This is, let's go ahead and call that definition 1. Now this is definition 2. The Taylor polynomial of degree n at x equals a for the function f is the sum from k equals 0 to n of the kth derivative of f, that's a k there, evaluated at a, not at 0, at a, over k factorial times x minus a to the k. And again, that's going to be a polynomial, this whole thing here, because it has just finitely many terms, it is a polynomial of degree n. If you don't believe me, you could actually take these terms, expand them out, and combine like terms, but you actually wouldn't want to do that with this. You actually want to leave these in the form where they have powers of x minus a, because that's a lot more informative usually about the behavior of the function near x equals a. Okay, so anyway, the whole idea here is if I wanted to find the Taylor polynomial of degree n for some function, let's say like f of x equals e to the x. So let's say we want to approximate this function, not near x equals 0, but let's say near x equals 1. Then what that would involve, it would involve going through finding the first few derivatives of this function at x equals 1. And because we know all of the derivatives of this function are just going to be e to the x, the first, second, third, all the derivatives at x equals 1 are going to be, at 1, are just going to be e. They're going to be e to the first power. So I could create a polynomial. So the nth Taylor polynomial for this function at x equals 1 is going to be the sum from k equals 0 to n of that kth derivative at 1, that's e to the 1, e, over k factorial times x minus 1 to the kth power. And that would be the nth degree Taylor polynomial at x equals 1. Okay, and that'll be a pretty terrific approximation for e to the x near x equals 1, but it might be lousy near x equals 0. It might not be that good anymore. I'm hoping that in class we'll have the chance to go over some of these and actually look at some of these polynomials on Desmos and see how they approximate this function f of x equals e to the x at different points. But that'll be something that we have to do together. And so there you have it. That was less than 6 minutes. I'm going to stop now while I'm ahead, and I will see you all in class.